Professor, can you hear me?
Yep, can you hear me okay?
Yep.
Awesome. All right. Good morning, everybody. I hope you've been enjoying the sun. It's been nice to have a little bit longer days these days as they keep going, and spring feels like it's right around the corner, which is so nice. Couple quick announcements. So we had our chapter 1 quiz. So now that the due date has passed, you can go back and review what you got right or wrong. I would strongly encourage you to stop by Drop In Help sometime just to go over the things you got wrong and talk about sort of why you got that wrong and strategies for multiple choice tests. In general, that's always a good idea. This week, we will be continuing with our chapter 2 work. So we started with limits and continuity, and we'll be continuing through chapter 2. I do want to mention that on Thursday, we're going to be doing some graphing. And so the reviews for this week on Thursday and Monday, the reviews that we're hosting each week, are going to be on graphing related to chapter 2. So if graphing is something in general that you have trouble with, or if on Thursday when we do more significant graphing, you're finding that's a little bit tricky, then those reviews will be really helpful. And so again, Thursday 5 to 6 and Monday 4 to 5, and then we will post the link to those after they are completed. So other than that, we're just sort of plugging along. This week is sort of a regular week. We have our mini quiz on Wednesday and Sunday, and our homework due on Sunday. And then next week, Monday is a holiday. And so Tuesday is a Monday schedule, which means next week, we won't have class on Tuesday. So I will remind you guys of that on Thursday, but otherwise, let's get rolling. Okay, so I'm going to switch over to the dot cam. Okay. So just as a reminder, what we were doing before, or last week, I suppose, is we looked at limits and continuity, right? We talked about this idea of closeness and getting close to something. And we're going to kind of incorporate that a little bit today. But a lot of the work that we're going to be doing is actually going to tie back to section 1.3, which we did 2.5 weeks ago, on the average rate of change. So I want you to remember that the average rate of change tells us how much a function changes on average between 2 points. And we use the formula f of b minus f of a over b minus a. And so that's sort of where we started our work after our sort of 1.1 review. And I mentioned during that class that the thing that we were building upon was this idea of the equation of a line. And so as a reminder, the average rate of change is the slope of a secant line. So when we do f of b minus f of a over b minus a, we were finding the slope of the line that connected those 2 points. Okay, so today we're going to build upon that. And we want to start developing this idea for what's called the instantaneous rate of change. And so the instantaneous rate of change is how much a function changes at 1 point. So again, the average rate of change is between 2 points, and what we're trying to get to is the instantaneous rate of change, which is how much the function changes at 1 point. And so what we do in order to try to develop and understand what's happening at 1 point is by looking at the average rate of change over smaller and smaller intervals and taking the limit as we get closer to the point we're interested in. Now, why would we want to do this? Well, we would want to do this because if we can determine how much a function is changing exactly at 1 point, we can then do that for all points. And instead of having an average rate of change, which is an approximation, we will have an actual rate of change for every point. Okay, and that's going to be more powerful. So we're basically trying to make our average rate of change better, if you will. So what's the difference sort of conceptually between average rate of change and instantaneous rate of change? So consider that you are going to take 3 hours and travel 150 miles to go to your cousin's house, right? Your average rate of change is going to be 50 miles per hour because you would take the distance, 150 miles, and divide it by the time, 3 hours. 150 divided by 3 gives you an average of 50 miles per hour. Okay, now we know that you were not going 50 miles per hour the entire time. Like right when you pulled off, you weren't going 50 miles per hour. It's your average over those 3 hours. Your instantaneous rate of change is going to be the reading on your speedometer at any given point, right? Like you look down and you're like, oh, I'm going 60 miles per hour. That's how much you're traveling in this moment. So that is an instantaneous rate of change. So at one point in time, okay? So how are we going to start thinking about it and developing this idea? So again, we're going to be using what we know, which now is the average rate of change, to help us develop and understand what we don't know quite yet, which is the instantaneous rate of change. So let's look at this picture for a moment. So here we are trying to figure out the instantaneous rate of change at -1, okay? So that's our sort of goal here. So x equals -1. We want to know what's happening there, okay? So what we're going to do to try to start to figure this out is we're going to use average rates of change. So we're going to look at where -1 hits our function, which is right here. And we're going to look at an average rate of change to the left and an average rate of change to the right to sort of see what's happening around our point, okay? So here, if I'm going to pick a point to the left, I want to go the same distance to the right. So here, when I pick a point to the left, I'm using -1 and -2 to pick my points here. And so when I do that, I'm going to be using the average rate of change to approximate the slope of this line. Okay, so if I were to write this with the formula, so I'm doing the average rate of change to the left of this point first, I'm going to do f of -1 minus f -2 divided by -1 minus -2, right? So f of b minus f of a over b minus a. So now I'm going to approximate those points. So at -1, right, I'm coming up here, and that looks like it is at 0.5 minus, now I'm going to do f of -2. So at -2, I go all the way up to this point, and I see that that has a value of 2 divided by, now again, be careful with the minus and negative, right? Negatives are always a little bit tricky. So that's going to give us a +1 on the bottom. So we crunch that number, 0.5 minus 2 divided by 1, and we get -1.5. So you can see that that is the slope of the average rate of change, 1 unit to the left. If we also look at this to the right, we can do the same thing. So different color. But again, since I went 1 full unit to the left, so -1 to -2, I'm going to go 1 full unit to the right, which will be -1 and 0. Okay, so when I do the average rate of change to the right, I have f of 0 minus f of -1 over 0 minus -1. Okay, so again, f of 0, I come here and I say, okay, 0 is going to give me 0. F of -1, we know is 0.5. And then on the bottom, 0 minus -1 is +1. So that's going to equal -0.5. Okay, so the slope to the right, the average rate of change, is -0.5. So I know how to find these average rates of change. So what did I do to apply that here? I have this point that I'm interested in, x equals -1. So I set up an average rate of change to the left and to the right. And the only sort of condition I imposed here is that I was the same distance away when I picked my average rate of change. So if I had gone 3 units away, I could go to -4 and +2, right? But what do these slopes tell us, right? So what happens is the instantaneous rate of change, so the amount that we're changing at this point, is going to be bounded by the average rate of change on the left and the right, which means it's going to need to be between negative 1.5 and negative 0.5. So that's on practicing sort of our average rate of change. But we also know that we want to start taking the limit and getting closer to the point we're interested in. So this is where this idea of closeness comes back. So what we're going to do is we're going to do this again, but instead of going all the way out 1 unit from -1, we're going to go 0.5 from -1. We're going to get closer on the left and the right to see what happens. And so before we do that, I just want to note, because we're going to circle back to this, that when we did it 1 unit away, that our instantaneous rate of change, I'm going to write it as IROC just because we don't have a lot of space, was bounded between negative 1.5 and negative 0.5, right? So that was the two values we got. Our instantaneous rate of change has to be between those two values. So let's see what happens when we do the average rates of change closer to -1. Okay, so I'm going to have you write out the calculations here to practice. I've drawn in the values and I'll draw sort of lines over. But now, again, we're interested in what's happening at -1. And so we're going to do the left. We're only going to go 0.5 to the left and 0.5 to the right instead of 1 whole unit. And so here, this is going to be roughly here. Okay, so you're going to be doing some approximations of where you think these things are and setting up your general f of b and f of a's. Okay, we can see that that is here. Okay, so we have these 3 points. So what I'd like you to do is I'd like you to take 2 minutes to do an approximation. I want you to do the left-hand approximation, which is the one in red. So the left is between -1 and -1.5. And I want you to do the right-hand approximation, which is between -1 and -0.5. I want you to set these up in the average rates of change and do a calculation and see how that compares to what we did when we were 1 unit away. Okay, so take 2 minutes to try to approximate the average rate of change for each of these, and then we will go through them together. Okay, take about 30 more seconds. All right. So when we look at the average rate of change to the left of -1, right? So we're considering what's going on, the -1. So when we look at the average rate of change to the left, we're only going half a unit this time instead of a full integer away. And so we're going to look between -1 and -1.5. So our general formula looks like this. And so now when we approximate these values, f of -1 is approximately 0.5. F of -1.5. So this one's a little bit trickier to approximate. So we may have slightly different numbers. I'm just going to talk to you about how I picked the number I picked. So I looked for like the halfway point, which to me seemed about here. And so halfway between 1 and 1.5 is 1.25. And then this to me looked like it was just about halfway between 1.25 and 1. So I used 1.125. If you use something like 1.2, that's fine, 1.3, but it should be somewhere, you know, in that general range, nothing really bigger than 1.3. So even that's a little high. But again, you may not have the same exact number, but it should be around that number. And then on the bottom, again, we have to be careful because we are subtracting a negative. We end up with positive 0.5 on the bottom. So when we crunch this number, we are going to get negative 1.25 on the left. So here, negative 1.25. And then we want to do the same thing on the right. We want to see what the slope of that line is so we can see what the average rate of change on the right looks like. Okay, so again, you know, we're looking in general here between the 2 points, -1 and -0.5. So if we just set up the formula using those. Okay. So now again, we have to do a little approximating. So f of -0.5, we come up here, right, to this little line here, and we're kind of trying to figure out where this value is. So I took a similar approach where, you know, the halfway point between 0 and 0.5 to me looks like it's right about here. So this is like 0.25. And so to me, that looked like it was just about halfway. So when I approximated that value, I used 0.125, which is halfway between 0 and 0.25. Again, you may not have used the same exact value, but it should be somewhere close. So you might have used 0.1, something like that. And then minus, and then f of -1, we said was 0.5. Divided by, and again, we're being extra careful with the negatives here. We get 0.5. And so when we crunch that number, we get -0.75. Okay, so here, slope is -0.75. One thing I do want to point out here is that both slopes are negative, which I was expecting because when I drew in these lines, they were going downward from left to right. So when the slope is negative, you expect to see a downward sloping line. So those match to me. So here now, I need to consider what this means in this context, right? So again, what this tells me is that my instantaneous rate of change has to be between these two values. So now I'm going to fill these in like I did before. So I have -1.25 and -0.75. Okay. And so what I'm noticing is that I'm getting closer in terms of my interval, right? So if I think about where -1.5 and -0.05 is on a number line, in order to get to my new interval, I would actually shrink within the number line. Okay, so there's a smaller span between these two numbers, which means that this is a more accurate approximation, okay, because the interval is smaller. Okay, and so what I want you to notice is that the difference between our two measurements was how far away we were from the point we were interested in, right? So in the first approximation we did, we were 1 unit away. In the second approximation, we were half a unit away, and we got a better approximation. So this is this idea of closeness. So the idea is that the closer that we get to -1 to do our approximation, the better our approximation is going to be. Because what we're aiming to do now is for our left-hand approximation to sort of come up in the scenario, and our right-hand approximation to get lower. And eventually, what's going to happen is that my left-hand approximation and my right-hand approximation are going to be so close that they become the same. Okay? And so our interval is shrinking until the upper bound and the lower bound are the same. And when that happens, that's where sort of the magic is. This is the limits coming back. We're, getting closer and closer to -1. But when that happens, when they come together to one line, we get the instantaneous rate of change. Okay. So again, when the left average rate of change and the right average rate of change become the same, we get the, I'm going to write this one out, instantaneous rate of change. Okay, so how do they become the same? We get closer and closer with our average rates of change, and eventually they approach the same value. Just like when we were looking at limits, if you look at these limits of average rates of change, they eventually approach the same value, which in this case is going to be -1, right? So if you think about the picture and the intervals we had a minute ago, we can see that -1 is on both of these intervals. It's in between the values we said it had to be in between. Okay, so our goal for now is going to be to think about how to approach this in different ways. How do we get closer and closer to the value we want so we can start getting better at either approximating or finding the instantaneous rate of change depending on the information we have. Now, the instantaneous rate of change has a lot of names, right, that we're going to talk about. But one of the things that's going to become really important to us is this idea of what this line is. This line when our two average rates of change, which were secant lines, come together to form one line. Okay, so when we have one line that touches at one point, this is called the tangent line. Okay, so a secant line connects 2 points, a tangent line touches at 1 point. Okay, so they're slightly different. And so the slope of the tangent line is our instantaneous rate of change. Okay, the slope of a secant line is the average rate of change. The slope of a tangent line is the instantaneous rate of change. An instantaneous rate of change is more accurate than average rate of change because instantaneous rate of change gives us the exact change at that point. Okay, so it's not an approximation if we have the instantaneous rate of change. Okay, so we want to think about how we can find the instantaneous rate of change and how we approximate the instantaneous rate of change and how this is going to come up in a whole bunch of ways. So we're going to start by looking at a table. Okay, and we're going to think about how we can use the average rate of change like we did on a picture to think about this data on a table. So consider that I've thrown a tennis ball up in the air and I have the ability to measure the height of the ball, which we're going to call S of t, in feet for each time in seconds. So every 1 second I am recording how high the ball has gone up. Okay, so the data is going to be recorded in this table. So again, I take the ball and I throw it up in the air. And so the minute I let go of the ball, right? The ball is 6 feet in the air, which makes sense. I'm like 5'6", and so when my arm is up in the air and I let go, it's about 6 feet in the air. Okay, so at time equals 0 is right when I let go of the ball. So at time equals 1, it has gone to 9 feet. After 2 seconds, it's gone to 11 feet. After 3 seconds, it's at 12 feet. And after 4 seconds, it's back down to 10 feet, right? Because it's going to start coming back down because of gravity. So we want to figure out the average rate of change to the left of 1. We want to figure out the average rate of change to the right of 1. And then we want to talk about how we can use that to talk about the instantaneous rate of change. So we know how to do average rates of change on a table from 1.3. So we're going to do that again. But I want to remind you, when you do an average rate of change on a table, you always want to use the closest point because that's going to be the most accurate. So when you do the average rate of change to the left, you're going to be using 1,9 and 0,6. And when you do it to the right, you'll use 1,9 and 2,11 because those are the closest points. So I want you to do the average rate of change to the left, the average rate of change to the right. If you finish that and you have time, think about what the units of those are going to be, and then think about how we might use that to talk about the instantaneous rate of change. Okay, so I'm going to give you 2 minutes, sketch that out, and then we will go through it together. Okay, take about 30 more seconds. Okay. So again, we're trying to figure out what we can learn about the instantaneous rate of change at 1. That's what we want to know about. We don't have a way yet to talk about the instantaneous rate of change at 1 on a table. So we're going to do what we did before with the graph, and we're going to use the average rate of change to the left and the average rate of change to the right to see what we can learn. Okay, so when we do the average rate of change to the left, the general formula will be f of 1 minus f of 0 over 1 minus 0, because again, we're using the point that's directly to the left. So f of 1 is 9, f of 0 is 6 divided by 1. So we get 3 over 1, which is going to be 3. Okay, let's take a minute to talk about units. So the units on the top for the 9 and the 6 are going to be in feet, and the units of the bottom, the 1 minus 0, are going to be in seconds. So this is 3 feet per second. Okay, that's how fast on average the ball is changing between 0 and 1. Now we also want to do the average rate of change to the right. So we do f of 2 minus f of 1 over 2 minus 1. F of 2 is going to give me 11. f of 1, we said was 9 over 2 minus 1, which is 1. So that gives me 2 feet per second. Okay, so I know the average rate of change to the left and the average rate of change to the right. Unfortunately, unlike the graph, I don't have a way right now to get closer to 1, right, on this table. This is the best I can do. We know that we want to get as close as possible to 1, but that's what we did when we did this 1 unit. Okay, so what do we know? We know that the instantaneous rate of change has to be between 2 and 3 feet per second. Okay, that is something we know. But if we had to make a best guess, given this information, right? If you are not able to get closer information, then your best guess for an instantaneous rate of change is going to be to average the left and the right together, right? So if I was like, you have to make a guess right now, right? We would take the 2 plus the 3, divide by 2. We would say, okay, 2.5 feet per second. Okay, we would average the left and the right to get our best guess for the instantaneous rate of change. And again, we only do a best guess if we can't get any closer to the value we're interested in, like we did here, right? We weren't able to get any closer. So instead, we average the left and the right to get our best guess for instantaneous rate of change. Okay, so keeping that in mind, right? Let's suppose that we could get closer to 1, right? What if somehow when I threw that ball, I was actually able to measure it every half a second, I could get the height, okay? We know that getting closer is better or more accurate. So let's say now that we have the data, but now we can get closer every half a second. I want you to notice that these are the same values we used last time, 0, 1, and 2. They have the same outputs here, the 11, the 9, and the 6. Only now we have additional information about where the ball is at 0.5 and at 1.5. So again, now that we can get closer to 1, we want to repeat our average rates of change to the left and the right with our closer information, and then use that and update our best guess for the instantaneous rate of change. So you're going to again do the average rate of change on the left and the right, and then you'll take those two values and average them to get your best guess for the instantaneous rate of change. Okay, so take another 2 minutes, sketch that out, and again, you're using the point right next to 1 now, and we'll see how that changes our best guess. Okay, so take 2 minutes and then we'll go through it together. Okay, take about 30 more seconds. All right, so let's see how getting closer to 1 impacts our calculations here. So again, we want to find the average rate of change to the left. So we'll do f of 1 minus f of 0.5 divided by 1 minus 0.5. f of 1 is 9, f of 0.5, 7.8 divided by 0.5. That's going to give us 2.4 feet per second. And then if we do the average rate of change to the right, f of 1.5 minus f of 1 over 1.5 minus 1, f of 1.5 is 10.1 minus f of 1 is 9 divided by 0.5. That's going to give us 2.2 feet per second. Okay, so as before we were between 2 and 3, now we know that we have to be between 2.4 and 2.2. That's a much smaller interval. That's only 0.2 in variance, right? That's a pretty close situation here, which means our approximation, again, is even better. So if we were going to use these to approximate, because we couldn't get any closer, our best guess is when we average these, and when you average 2.4 and 2.2, you get 2.3 feet per second. Okay, so we've updated it. Before, our best guess was 2.5, and our span was 2 to 3. Now our guess is 2.3, where our span is 2.2 to 2.4, right? So this is definitely much closer to the actual instantaneous rate of change. And again, this is the best we can do with this table because we can't get any closer. But again, what happens if we could, right? If we could, we should. So let's now assume that somebody with excellent tools, all the best tools in measuring heights, is able to measure the height at 0.99 seconds, 1 second, and 1.01 seconds, right? So they can measure it every 1/100th of a second, right? Which is incredible. So here, if we now have the same data, so again, at 1, we know we're at 9 feet, that didn't change. But at 0.99, we know how high we were, so 8.976355. And at 1.01, we have 9.023645. So again, we're going to take the average rate of change to the left, average rate of change to the right, and then we're going to see what those look like in comparison to our last calculation. So now we are much, much closer. So we're expecting our approximations to shrink even more in terms of an interval, and we will get an even better approximation. Okay, so you're going to do it to the left, you're going to do it to the right, and then we're going to see what shakes out. Okay, so take 2 minutes, be careful with the teeny tiny decimals as you plug them in, and then see what sorts of interesting things happen here. Okay, so 2 minutes, and then we'll go through it together. Okay, take about 30 seconds. All right. So I do want to point out that when we start working with smaller and smaller numbers that have a lot of decimals, it's really easy to mistype something or forget parentheses. So just be extra careful when you're working with teeny tiny numbers. So when we do the average rate of change to the left, we have f of 1, which is 9, minus f of 0.99, which is our 8.976355, divided by 1 minus 0.99, which is 0.01. Okay, so we're going to plug that all into the calculator, and we're going to get 2.3645 feet per second. And then when we do this on the right, 1.01, that's going to give us this 9.023645 minus f of 1, which is 9, divided by 0.01, which is going to give us 2.3645, right? So these two agree to the first 4 decimal places, okay? And so if you have something that overlaps this much on the first 4 decimal places, then you are pretty sure that you can say your instantaneous rate of change has to be 2.3645, because if the slope to the left is the same as the slope to the right, that's when we have our instantaneous rate of change. So this is the same number, okay? So we can say that our instantaneous rate of change is 2.3645. Okay, and typically we want to see at least 2 matching decimal places, but the more the better, right? So if we had 2.36 and 2.36 here, but then different decimals after, then we would say 2.36, right? If we match the first 2 decimals, that is good enough for our instantaneous rate of change. If we happen to get more, even better. Okay, so we had guessed 2.3 here because we knew we had to be between 2.2 and 2.4, but now we know it's actually 2.3645 is our instantaneous rate of change. So there's a couple things that we need to think about and remember when we're talking about instantaneous rate of change. So as I mentioned, the instantaneous rate of change has a lot of names. So far when we talked about the instantaneous rate of change, we really want to remember that it's the slope of the tangent line. Okay, so even though we're doing all these calculations in the background, what we are actually calculating is the slope of the tangent line, which is the line that touches whatever this function is at 1. So if we were to draw it in, if we were able to draw this function, we would draw on the line that touches just at 1, and this calculation we're doing is finding the slope of that tangent line. Now, we also call the instantaneous rate of change the derivative. Okay, so this is another word that means the same thing as instantaneous rate of change. And so I want to take a minute to talk about why we have 2 different words that mean the same exact thing. Okay, so when calculus was being discovered, this was like the late 1600s, I think during some sort of plague, right? There were 2 men who developed calculus at the same time, right? It was very controversial. So there was Isaac Newton and Gottfried Leibniz. And they were working, and Newton accused Leibniz of stealing his work, but Newton hadn't published it. It was very controversial for the times. They had big, goofy looking wigs, all that sort of stuff. So essentially, no one ever settled this debate. And the result is that we just have two different sets of notation and terminology for the things that we do in calculus, because no one ever came down on one side. So we just sort of accept it all. So if you are in physics, you'll often see the Newtonian notation. If you are in engineering, you're more likely to see the Leibniz notation. In math, we use both, which is really confusing. But these are the same thing. So the derivative, which is the Newtonian word for it, uses the notation f prime of a. Okay, so what this means is that we are approximating the instantaneous rate of change at the value a. So that means when we were up here doing this calculation, we were approximating f prime of 1, because 1 was the number we were looking around. Okay, so this f prime is another way to indicate you are looking for the instantaneous rate of change. Okay, now another way you're going to see this notated for the instantaneous rate of change, so the mathematical notation for Leibniz is often written as dy dx, which means the derivative of y with respect to x. Now, this is helpful. This notation is helpful when we think about units, because we do the units of the dependent variable over the units of the independent variable. So that helps us remember the units. But this is the notation that is the same as this notation. Okay, we use them both. In this class, we tend to use this notation more unless we're specifically looking for units. Then we might use this, but they mean the same thing. And it's important that you recognize them both, because if you go to another class and they want to talk about it, they could use either of these. And we need to remember that both of them mean the same thing, that we're looking for the instantaneous rate of change. Okay, so now that we've sort of talked about notation, and I'll remind you as we go about the notation, let's go ahead and look at this problem here. So we're going to use the table below, and we're going to approximate the instantaneous rate of change, just like we did on the last couple of tables, but we're going to approximate it for all the points on this table. So for 1, for 2, for 3, for 4, and for 5. And so a couple things I want to point out. When you approximate at an endpoint, you can't do the left and the right, right? Because there's not one of those existing. So like when you approximate for 1, there is no left-hand point. So you can only use the point to the right. So you're going to do the average rate of change to the right to get your approximation for 1. When you do the 5, you can only use the left point. So you're going to do the average rate of change to the left to approximate for 5. Now, when you're in the middle of the table, you would do the left and the right and then average them together. Or what you can do is you can do the average rate of change around the point. So you would use 3 and 31 and 1 and 7, and that would give you the average rate of change for 2, because what it does is it does the left and the right and then averages them together. Okay, so you'll get the same value if you do the left and then the right, and then you average them together, or if you do it around the 2. Either way is fine. So you're going to approximate the instantaneous rate of change for every single value on this table. And we're going to create sort of a new row. We've done lots of average rates of change on tables when we were looking for concavity, but now this is a better approximation, right? Because instead of doing the average rate of change between 1 and 2 and getting something between them, we are approximating it at the point by looking left and right and averaging them. Okay, so I'm going to give you 2 to 3 minutes to find each of these. It's really good practice to do these average rates of change. So do them out, fill out the table, and then we will go through it together. Okay, take about 30 more seconds. All right, so let's go through these really quickly. So again, when you're doing the derivative for 1, you can only use the point next to it because there is no point to the left. So when we do the average rate of change, we'll do f of 2 minus f of 1 over 2 minus 1. That's going to give us 16 minus 7 divided by 2 minus 1, which is going to give us 9. So our approximation for the derivative at 1 is going to be 9. Similarly, we're going to do the same thing for 5. We're going to jump down to the other end and do the 2 endpoints first. You don't have to do it that way. It's just how I set it up. So here we're just going to use the point to the left because there is no point to the right. So here we're going to do f of 5 minus f of 4 over 5 minus 4. F of 5 is 79. F of 4 is 52 divided by 5 minus 4. That's going to give us 27. For our f prime of 5. Now, for the middle values, you can either do the left and the right and average them together, or, as I was trying to say, you can do the points around them. So for f prime of 2, you can do the left and then the right and then average them. That's totally fine. But you can also do the 2 points directly next to them. So we can do f of 3 minus f of 1 over 3 minus 1. So we get 31 minus 7, which is 24, divided by 2 is going to give us 12. You will get the same thing if you do the average rate of change to the left and then to the right, and then average those two numbers together. For 3, we're going to do something similar where we're going to go around it. So we're going to do f of 4 minus f of 2 over 4 minus 2. So here f of 4 was 52, f of 2 was 16, divided by 2. So 52 minus 16 is going to give us 36 divided by 2 is 18. And then finally, for f of 4, we'll do that one in blue. We're going to do f of 5 minus f of 3 over 5 minus 3. And again, if you don't want to go around it, you can do the left and the right and average them together. It just takes a couple extra calculations. So here, f of 5 is 79 minus, now f of 3 is 31, divided by 5 minus 3 is going to give us 2. So if we subtract those, that's going to give us 48 divided by 2, which is going to be 24. Okay, so we've approximated the derivative for every point on the table. Now, it's really important that we understand that this approximation is better than the average rate of change approximations we were looking at before. Okay, it doesn't mean we can't do a general average rate of change down the table between every 2 points. But when we use the left and the right to come up with an approximation, it's a little bit better. Okay, so we've approximated the derivative at every single point on the table. This is something that we do quite often in this class. So we want to get really good at finding the derivative for a table and setting it up like this, where we write the derivative in its own row underneath, because there's a lot of implications which we'll get to sort of at the end of chapter 2 about the behavior and what that looks like if we consider all of these together, right? Because we're finding the average and average rate of change to find the instantaneous rates of change at a point, but then at some point we're going to consider all of these points in a bigger context. Okay, so the next thing we want to consider is we really want to relate this back to the slope of the tangent line. Okay, so we have this graph below of f of x, and we want to look at each of these possible derivatives and determine, is the derivative going to be positive, negative, or zero? And so again, we have to remember that the derivative is the slope of the tangent line. So what we need to do is we need to think about what that tangent line is going to look like at each of these points to figure out if they'll be positive, negative, or zero. So we'll do one of them together, and then you'll try the other ones. So f prime of -2. So the instantaneous rate of change at -2. So we go to -2, we figure out where that point is, and then we sort of visualize or even draw in a little tangent line here, which is going to look something like this. The tangent line, right, touches at that one point. And then we look at that line and say, is the slope of that line positive, negative, or zero? So this one is going down from left to right. So the slope of this line is negative. So the derivative is negative. We're not going to calculate right now what that slope is. We just want to know, is it positive, negative, or zero? So positive slopes have lines that are going up from left to right, negative going down from left to right, and a slope of zero would be a horizontal line. Okay, so I want you to take a minute and a half. We're going to look at f prime of -1. So I'll draw on the dot so you can see where these things are, just in case you can't see the scale. So -1. And then we have 0, which is here. We have +1, which is here. And then finally, we have 2, which is here. So try to envision what the tangent lines are going to look like, and then determine if the slope of that line will be positive, negative, or zero. Okay, so I'm going to give you about a minute and a half to look at that, to try to think about it, see what you can come up with, and then we'll sketch some tangent lines in and see what shakes out. Okay, take about 30 more seconds. All right. So the goal here is just to start imagining what these tangent lines are going to look like, so we can figure out if they're going up, down, or horizontally. So at -1, if we were to draw on the tangent line, it would look something like this, and we can see it's going up from left to right. That tells me that if I were able to calculate the slope of this line, that it would be a positive number. Okay. At 0, when I draw on the tangent line, it ends up sitting on it like a table. It balances right on top of this hill. And so this tangent line has a slope of 0 because it's horizontal, right? It's right along the axis here. At 1, if I were to sketch in a tangent line, it would look like this, which is going downward from left to right. So that one's going to be negative. And then the last one at 2, we see is going to go upward from left to right. So that's going to be positive. So we start off this way by figuring out if things are going to be positive, negative, or 0. And then by the end of chapter 2, we will know how to calculate the slopes of these lines more precisely. Obviously, if you're really comfortable with lines, you know that if we were to draw on this line, we could just pick points on the line to get the slope, but we're not quite there yet. So for right now, we want to know positive, negative, or 0. So you should get really comfortable with the way lines are sloped and looking at them and knowing if they're positive, negative, or 0. Okay. So far we've looked at tables and things that were given to us precisely. Sometimes we need to find the instantaneous rate of change by setting up our own tables. So let's say we wanted to approximate the instantaneous rate of change for the function 4x squared at x equals 3. Which is the same thing as if we used the notation f prime of 3. So since we are still approximating right now and trying to understand how to get close to things using average rates of change, what we're going to do is we're going to set up our own table. We have our x value, we have our f of x values. And just like we had in the tables before, we want the value that we're interested in the middle, and then we want to get close to it on the left and close to it on the right by the same distance, right? So if we were to go 1 full integer to the left, we would go 1 full integer to the right, but we know that that's not what it means to be close. So what I would recommend for closeness is something like 2.99 and 3.01. You could use 2.9 and 3.1, that's fine. But the thing here is that we're setting up our own table. So what we need to do is plug each of these values into this function to get the corresponding dependent value. So that's going to be the first step, is to plug in these other values into 4x squared to get the dependent values. Then we're going to use those, and we're going to do an average rate of change on the left and an average rate of change on the right, so that we can get a good approximation for what our instantaneous rate of change is going to be here. Okay, so take about 2.5 minutes. Again, first we need to make our table. I picked these numbers, these weren't given, right? We need to plug those into the function, then we can do our average rates of change on the left and the right. So try that out, and then we will go through it together. Okay, take about 30 more seconds. Okay. So again, when we're approximating, we are setting up our own table, and I'm going to make some comments about this after, but I want to finish the actual calculation here. So I used 2.99 and 3.01. Then I found the dependent values by plugging those into my function. And now I'm going to do the average rate of change on the left and the average rate of change on the right. So when I do it on the left, I'll do 36 minus 35.7604 divided by 0.01. When I do that, I'm going to get 23.96. And when I do the average rate of change on the right, I get 24.02. So my instantaneous rate of change, which I can call f prime of 3, is approximately the average of these two numbers. So I'm going to average those two numbers, and I get 23.99. Okay. So I set up my own table. I want to point out that oftentimes in homework or on Wiley or Wiley's homework or on the mini quizzes, you are going to be told how far to look. And the notation that we use for that is delta. So delta equals 0.1, right? So you might see delta x in this situation, delta t if the variable was t. So it might say something like approximate the instantaneous rate of change for 4x squared at x equals 3 using delta x equals 0.01. So that means you have to go within 1/100th on either side. If delta x was 0.1, then you would use 2.9 and 3.1, right? So oftentimes in the problem, it's going to tell you what to use because that's the only way we're going to make sure you're getting the same answer that is listed on the quiz. And the other thing that happens sometimes is sometimes you are asked specifically to use the left or the right instead of both. So you could have a situation that says approximate the instantaneous rate of change using delta equals 0.01 using a right-hand approximation. So if it's listed, then you just take the one on the right. If it doesn't say left or right, that's when you do both and you average them together. Okay, so that's just some sort of small ways that this could be adapted. Now, I'm just going to talk about these real quick. We're not going to have enough time to do them. Example 4, you set up the same way as example 3. So we have a different type of function, but you're setting up your own table. And it's going to center around the value of 2, because in this problem, we're talking about years since 2010, and we want to know what's happening in 2012. So you're going to use 1.99, 2.01, and do the same process where you plug these into the function to get the dependent values, and then do the average rate of change. Okay, so that's going to set up the same way. The last one I want to talk about is different. So here we have this function f of x, and we see that the tangent line has been drawn in, and the tangent line touches at A. Okay, so C and B are on the tangent line, but A is where it actually touches the function. So we're told here that for the function below, f of 4 equals 25. So that's this point A, right? 4 comma 25, because we see that the 4 goes up and that's where that A value is. We also know that f prime of 4 equals 1.5. So that means the slope of this tangent line is 1.5. So we have a line with a slope and a point, and we want to use this to find A and B. So what we need to do is find the equation of this line using y equals mx plus b. M is the slope, so 1.5x plus b. We're going to use the point that's on this line, which is 425. So 25 goes here, 4 goes here. We use that to solve for b. So this is 6. So we subtract 6 from both sides. So we have b equals 19. So the equation of this line is 1.5x plus 19. So if we want to find c, the coordinates for c, we would take 3.9 and plug it in for x, and then we'd get the y value. To get the coordinates for b, we would take 4.2 and plug it in for x, and that would give us the y value. But we had to use the mechanisms we know about this line to get the equation of the line so that we could then plug in the values we needed to. Okay, so that's just sort of a sketch of how that one works. There is one like this on your homework. So if you'd like to see this done out in more detail, it is in the asynchronous lecture videos that's posted on Moodle. Okay, so that will wrap up what we're doing for today with instantaneous rate of change. Practice this as much as you can. It'll be really helpful if you do the homework on this before Thursday, because we are going to be building onto this. So the better you know this, the more smoothly Thursday will go. Okay, have a great rest of your day, and I will see you guys in 2 days.